Hello, everyone. Our work focuses on the practical detection of Trojan neural networks in the data-limited and data-free cases. First, let's see what is Trojan attack. Here is a simple example. We have clean training data set of traffic signs, and we use this data together with their true labels to train a model. We then obtain a clean model, which makes predictions accurately given normal inputs. Now attackers can poison a small portion of training data set by adding a Trojan trigger on clean data and change their labels to the target label. After training model with clean data and poison data, we obtain a Trojan model. A Trojan model also makes correct predictions to normal inputs, but once the data is stamped with the Trojan trigger, the model prediction is a fixed target label. Here, the target label is the speed limit sign. You can see that the Trojan triggers are added to images by replacing certain pixels of the original images. It could be a pixel, a cross, or even a watermark. We point out that the dangers of Trojan AI models can indeed happen in real life. Especially many users acquire models from vendors or open model repositories. And in many cases, number of data is limited to users. Our goal is to detect an AI model with minimal information about the AI's problem domain, specifically in the scenario of limited data. In our work, we first propose a data-limited Trojan net detector, when only a few data samples are available for Trojan model detection. In addition, we propose a data-free Trojan net detector, which allows users to detect Trojan model without accessing any data samples. Our detectors can not only reach good detection performance, but can also review the real trigger pattern. Current works on Trojan model detection without accessing to training dataset all fall into one or more restrictions. For example, additional costs to train detection model, restrictions on CNN model architectures. Our methods can overcome these drawbacks and provide efficient and accurate detection. Let's first take a look at data-limited Trojan net detector. Here's the CNN model and some clean test data. We know that the real Trojan trigger can make all the data transform to the target label. So our first observation is that there exists a small perturbation for all the data transforming to the target label under a Trojan model. In our framework, for each class, we will find a universal perturbation for all the data and a per image perturbation for each data through some optimization methods. Note that under a Trojan model, if the two different perturbations can make data transform to the target class, then the perturbations will all contain information of the Trojan trigger and show high similarity. This property only happens under a Trojan model and can be leveraged for model detection. We call the output before the fully connect layer as a neuron activation. Here, the similarity of the perturbations is measured using their neuron activation vectors. Next, we will show how to obtain the universal perturbation and per image perturbations. We will test each label to check whether it is a target label. When we test label K, we first separate the data into two parts. The first set dk contains data belonging to label K. The second set dk minus contains data not belonging to label K. The universal perturbation for label K is calculated by minimizing the following optimization objective. The perturbation is characterized by the binary mask M and the magnitude delta, where M represents whether to replace a pixel or not. Delta represents the replacing magnitude. X and X hat are the original image and the recovered image respectively. If K indeed is a target label, the ideal perturbation should transform all the data to class K. Therefore, the universal perturbation should transform all the data in dk minors to a different class from their ground truth, and keep data in dk not changing their labels. We also have a sparse penalty term to restrict the area of the perturbation. Note that if the model is a Trojan model and K indeed is a target label, then after the optimization, data in dk minors should transform to the target class with high probability, since we know there exists a small perturbation there. Then the optimization objective of the per image perturbation forces each data to transform to class K. We test all the classes until we find the target label. Once we obtain the two different perturbations in each class, we can measure their similarity by comparing their neuron activation vectors. One can see from the top figure that the neuron activation vectors under two different perturbations show high similarity if the test label K is a target label. For each data point, we can obtain a similarity value when testing each class. Then we can draw the distribution of the similarity values in each class under a Trojan model and a clean model. From the bottom figure, one can see that only the target class under a Trojan model has all similarity values close to 1. Then we could use the median of the similarity values in each class as a detection index. Here we show some of our results. The left figure shows the universal perturbations we found under target classes of Trojan models and some classes of clean models. One can see that the perturbations show similar patterns of the real Trojan triggers under Trojan models, while clean models do not have such property. We also test the detector under different model architectures, different data sets, and different triggers. The right figures show that the data-limited Trojan net detector can reach near perfect AUC values, and the detection performance outperforms the existing method neural cleans. Now let's see the data-free Trojan net detector. This detector allows users to detect Trojan models with random seed images. Existing works show that the neural activation vector has high L infinity norm if the input contains Trojan trigger. This indicates that some coordinates of the neuron activation correspond to Trojan trigger. We also know that the input with the Trojan trigger will always be predicted to the target label, which indicates the robustness of the Trojan feature. Considering the relation between the unexpectedly high neurons activation and the Trojan trigger robustness, we would like to ask, can we find the Trojan trigger and then detect the model by maximizing the neuron activation vector with a perturbation in the input? And will this perturbation finally show the pattern of the real Trojan trigger? Here is our optimization problem based on the previous framework. Ri is a value of the ith coordinate of the neuron activation vector. We try to find the perturbation by maximizing the weight sum of the neuron activation vectors. If the model is a Trojan model, then the Trojan-related coordinates together with their weights will have large value after the optimization, while other coordinates and the weights will have small values. In the bottom figure, one can see that by solving this optimization problem with random seed images, the perturbations we find indeed shows the patterns of the real Trojan trigger under a Trojan model. We'll have random behaviors under a clean model. Once we obtain the recovered data, we can calculate the difference between the largest layer output of the recovered data and the original data. Because we already know that the perturbation we found under a Trojan model contain information of the Trojan trigger. So in this case, the largest output corresponding to the target class show a significantly large increase comparing to other classes. One can also check from the left figure that the largest output increases of a clean model don't have such large value gap. This suggests that we could use the increase of the largest layer output as a detection index. Here, the left figure shows that the data-free Trojan net detector can review Trojan trigger patterns under different data sets and triggers. One can compare the similarity between the last row and the next to last row. The pattern shift phenomenon is because of the convolutional operations. As a contrast, the recovered perturbation in the third row show random behaviors, indicate that the models are clean. The right figures show that data-free Trojan net detector also has good detection performance under different attack success rates. In addition, we show that data-free Trojan net detector can work on clean label attack, which is a kind of attack that does not have explicit triggers. Our future directions include 3 parts: extend our detector to more complex scenarios, find approaches to mitigate the trigger, and develop theoretical analysis. Thank you for watching.